Our last lesson is about solving problems with exponential and logarithmic functions. So these are problems that we need to model. The first type is modeling exponential growth and decay. The general formula for exponential growth and decay can be found right here. And it's y equals k times a to the exponent t over n. Y being the final amount, k being the initial amount, a being the change factor. So that's by how much the initial amount is growing or decaying each time it grows or decays. The exponent is t divided by n, and it's the number of times the value changes, often a fraction. So that is made up in two parts, t being the time and n being the time period. So for example, if we have exponential growth, say by 5% every 3 hours, your time is probably a time in hours, and your time period is 3 hours, because it grows by that 5% every 3 hours. A being the base of our exponent here. If a is greater than 1, we have a growth model, and if a is somewhere between 0 and 1, we have decay, because that repeated multiplication, or that exponent, would be a value with a base less than 1. So we'd be constantly multiplying by something less than 1, which would decrease our initial value. Constantly multiplying by something bigger than 1 would increase the value. That's why we have growth. So we're going to do 3 examples here, 2 for growth, 1 for decay. And we're going to work on picking out the pieces from the word problem to fill in our model. So we're always going to start with that equation, y equals k times a to the exponent t over n. And we're going to try to pick out the pieces from the word problem to fill in what we have, and then determine what we need to find. So it says a certain cell is allowed to divide after 4 hours. It is estimated that there are 10,000 cells. If the number of cells doubles every 2 hours, how many cells were there originally? So what information do we have here? Well, we know that the cell amount doubles, and doubling would be our change factor. We're doubling, and doubling means we're multiplying by 2. So A, our change factor, is 2. Cells doubling, that's A. They're allowed to divide every 4 hours. So every 4 hours, they're allowed to divide, and after 4 hours it was estimated that there are 10,000 cells. So sorry, it doesn't divide every 4 hours. It actually doubles every 2 hours. So it's been dividing for 4 hours, but it doubles every 2 hours. So every 2 hours would be your time period n, and 4 hours of dividing would be your time t. So our exponent is 4 divided by 2, or t divided by n. 4 divided by 2 is simply 2. So it looks like it's doubled twice, once after 2 hours and once again after the 4 hours. It's estimated that there are 10,000 cells, and we want to know how much there are originally. So the 10,000 cells is actually our y, and how many there were originally, we're looking for k. We don't know what k is. So we have 10,000 equals k. So to solve for k, we actually just have to do a little bit of rearranging here. 2 to the exponent 2 is 4, so we actually have 4k equals 10,000. And if we divide both sides by 4, we get 2,500. And that's how many cells there were originally. So we can write a nice therefore statement. Therefore, there were 2,500 cells originally. Perfect. Example 2 is a similar question. We're going to model it the same way. It says, how long does it take for an investment of $500 to double at 7% interest compounded annually? So we've got a few pieces of information here. We know how long does it take for an investment of 500 So we know that this is going to be our initial amount, k. Our equation is going to look like y equals k times a to the exponent t over n. We want to know how much, how long it takes for the amount to double. So this double tells us something about y. We want to know how long until we have $1,000. So we now know y is 1,000. K was 500. Do we know anything about A? Well, we know that we're increasing by 7% each year. So our growth factor, or by how much we're changing, would be up 7%. So A would be 1 plus our growth factor of 0.07, or 7%. So A is 1.07. Why is it 1.07? Well, for it to be growth, we need to be a value bigger than 1. Multiplying any number by 1 gives us our original amount back, so that would be our original amount of 500. Multiplying by 7% will give us how much we're going up by each year. So multiplying by 1.07 will give us the original 500 plus how much we're going up by 7% each year. So our growth factor is, our change factor is 1.07. What do we know about our exponent? Well, we know that it's interest compounded annually, so it's per year, so t per year, or t divided by 1, which is just t. So in this case, we're actually solving for the exponent. So we can do a little bit of manipulation here. We can divide both sides by 500 first, and this is something that we would have done in grade 11 as well. But in grade 11, we got to this point, and the strategy we had was guess and check. Now, with the knowledge of logarithms, we can actually solve this by taking the log of both sides. You can use the natural logarithm, or you can use the common logarithm. I'm going to use the common logarithm, so log base 10 of 2 equals log of 1.07t. Why take the log of both sides? Well, in the solving logarithmic equations, we discussed that taking the log of both sides allowed us to use the power rule for logarithms to help us isolate for our exponent. So we can rewrite this as t times the log of 1.07 equal to log 2. And now to isolate for t, we actually just have to divide both sides by log of 1.07. That will eliminate the log of 1.07 on the right side, isolating for t. And it'll leave us with something on the left side that we can just punch into our calculator. So t is log 2 divided by log 1.07. And if we punch that into our calculator, we get approximately 10.2 years. So therefore, it would take 10.2 years to double your investment at 7% interest. All right. Example 3. This one is a decay question. It says, how long will it take for an isotope of sodium to decrease to 35% of its initial level if its half-life is 5.32 days? All right, we're going to use the same model, y equals k times a to the exponent t over n. What pieces do we have here? Well, we have a half-life, so that's going to be our change factor, because the amount is going to be cut in half every 5.32 days. So A is our half-life, which is our change factor. So A is a half. 5.32 days, that's how long it takes to decay in half. So that's actually our time period. So we have t over 5.32 0.32. And here we don't know anything specifically about how much sodium there was at the beginning and how much we have at the end. We do know that we want it for when it decreases to 35%. So there's a couple ways you can do that. Is you can start with an initial amount of 100% and then write your final amount as 35%. You could start with an initial amount of 1, say, gram of sodium and then have 0.35 grams of sodium in the future as our final value. It's up to you what you use. I think it's easiest just to use 135 for argument's sake, but you'll see it simplifies down to the same thing anyway. So let's call our initial amount 100 as 100% and our final amount of 35. So when we start to isolate here, we'll divide both sides by 100 first, and that would give us 0.35, or our 35% is our final amount, and 1/2 to the exponent t over 5.32. And now, again, we're solving for the exponent. So the strategy we used in example 2 is the same for our strategy here in example 3. We're going to take the log of both sides. I'm going to use the common logarithm again. So we'll do log of 0.35 equals the log of 1/2 to the exponent t over 5.32. And we take the log of both sides, so we can use the power rule and bring our exponent down. The reason we want to bring our exponent down is because we're solving for t, so we're trying to isolate for t. Bringing it out of an exponent allows us to not just guess and check, but actually evaluate for t. Solve for t directly. So on our left side, we have log of 0.35, and on our right side, if we use the power rule for logarithms, we have t over 5.32 times log of 1/2. To fully isolate for t, we'll multiply both sides by 5.32, which will eliminate the 5.32 on the right side, and we'll divide both sides by log of 1/2 to isolate for t. Call it log 0.5. And now this is just a number that we can punch into our calculator, and that will give us an approximate solution for t, which is 8.06. 8.06 what? Well, the units will be the same as the units for the time period, so the units are days. So therefore, it would take 8.06 days for an isotope of sodium to decay to 35% of its original level. Okay, that's using exponential equations to model exponential problems and then to solve using these exponential models.